At 14, I better mark these. Got 2 of them coming up. Number 1. Which of the following is a conjugate acid-base pair? Remember what's required for an acid-base pair to be conjugate of one another. First of all, you have to have one of them has to be an acid, of course, and the other, the base, would be what's left over after that one hydrogen is removed. Okay, so you have to have these parts to be the same, and only one of these hydrogens can be removed at a time. Okay, so the first one meets this condition where you have hydrogen, but the A's are not the same. Chloride versus hypochlorite. Right, so that one doesn't work. The second one, sulfuric acid, has lost 2 protons. That can't work, because you can only have one at a time. The third one, we have ammonium here, and it does lose 1 proton. So that meets both conditions. Okay. And the last one, of course, has lost 2 protons to get to the OH minus. In other words, H3O plus and OH minus. Instead of 3 here and 1 there, that means you've lost 2 protons. It can't work. So C works, D doesn't work, and more than one of these. No, just one of them is true. And let's see here. Board is going to be difficult today. Number 2. A hydrogen sulfate or bisulfate, HSO4 minus, it's a polyatomic ion, can act as either an acid or a base in water solution. In which of the following equations does HSO4 minus act as an acid? We can write that out and then go look for the answer. If it's going to be an acid, and this is the abbreviated form, remember, you transfer protons to water or something else to a base. But to keep things simple, we're just going to remove a hydrogen, recognizing that that's not really what happens in solution. So, okay, I missed my guess. They're actually doing what really happens. So this is going to be H3 plus. There we go. That's what it should look like if it's an acid. So the one that comes closest to that one, let's see. It's either A or D, if water is the base. And then looks like D works the best. Yeah. Does that make sense? Okay. All right, go to number 3. That's better. Okay, which of the following is the equilibrium constant expression for the dissociation of weak acid HOCl? Well, I can tell from looking at the answers that this is going to be the abbreviated form. So we're just going to take hypochlorous acid, and I'm leaving out the aqueous part, and remove a proton. Okay. So the equilibrium expression here, Ka is going to be hydrogens conjugate base divided by the undissociated acid. Okay. And it looks like A is the best one for that. Moving along. Let's see. How about number 6? A solution in which the pOH is 12.1 would be described as. If the pOH equals 12.1. Okay. I think of acid base in terms of pH. So what I would do is say pH is equal to 14 minus 12.1, which would be, let's see, 1.9. Yeah, that's an acidic solution, a very acidic solution. So A is the best answer there. I don't think in terms of pOH, it just doesn't click. So if I put it in terms of pH, then it makes sense. Number 7. Which of the following indicates the most basic solution? Okay, so we got several different approaches that have to be rectified so that we can compare apples and apples. All right, the first one is hydrogen ions 1 times 10 to the minus 10. Molar. All right, we know that 10 to the minus 7 is neutral. Anything greater than that is acidic. So this has to be basic. We could convert it to pH, right? pH would be 10. Right? Negative log of 10 to the minus 10 is 10. pOH is 6.7. pOH equals 6.7. Well, pH is going to be 14 minus 6.7 equals, let's see, 7.3. So that's basic also. Slightly basic. And then hydroxide as 7 times 10 to the minus 5. 7 times 10 to the minus 5 molar. Similar to our logic for this one, if hydroxide concentration is 10 to the minus 7, it's neutral. But this is much, much greater than 10 to the minus 7. So that means it's basic. And D, pH 4.2. That's acidic. No doubt about that one. There she is. At least 2 of the solutions are equally basic. Are equally basic. No. There are none of them that are equally basic. Right. This would be 10 to the minus 4 hydroxide. This is 10 to the minus 5 hydroxide. This is almost neutral. So E can't be it, because there are no 2 basic ones that are exactly equal. Okay. So which is the most basic? Well, let's see. Hold on a second. Indicates the most basic solution. Oh, okay. So we would have to do a calculation here. This would be 10 to the minus 4 molar. Because 10 to the minus 10 times 10 to the minus 4 is 10 to the minus 14, which is required for Kw equals 1 times 10 to the minus 14. And that's equal to the hydrogen ion concentration times the hydroxide concentration. So if this is 10 to the minus 10, that one has to be 10 to the minus 4. Did I lose you? Okay. This is definition for KW. The equilibrium constant for water, which is hydrogen ion times hydroxyls. If we substitute 10 to the minus 10 here, and this has to be equal to 10 to the minus 14, how do we get there? Well, when you multiply two powers together and they're the same base, then you just add the exponents. So that makes this one 10 to the minus 4. Okay, 10 to the minus 4, this is going to be approximately 10 to the minus 7. It'll be a little bit greater than that. Let's say greater than 10 to the minus 7, but not much. And this one's 10 to the minus 5. So 10 to the minus 4 is the greatest one of those three. That's why A is the strongest base. Okay, number 8. Which of the following solutions contains the strongest acid? Okay, let's see. We've got, all right, 7 was the most basic solution. So that was dependent upon the concentration. We could do that calculation. When we say strongest acid or strongest base, we're talking about an intensive property. And that refers to the equilibrium. So the equilibrium constant will tell us which is the strongest acid, right? Are all those Kas? Yes, everyone is a Ka. So what we're looking for is the Ka with the largest value, because the numerator is the product where the hydrogen ions are located. So the largest value of Ka is going to tell us the strongest acid. And there's one in there that has an A1 and an A2. But you'll notice that the A2 is 7 orders of magnitude weaker than the first one. So that means the second one has no impact on the acidity. So all we have to do is look at the values of the Ka1. And if we just compare the powers of 10. First one is 10 to the minus 10, second one's 10 to the minus 5. C is 10 to the minus 5, 10 to the minus 8, 10 to the minus 4. The last one is 10 to the minus 4. It's greater than any of them. So the answer is E, which is HF. Now suppose HF wasn't there. Suppose we had something else, like with a 10 to the minus 13, right? Then we would have to look at B and C, because they have both 10 to the minus 5. And then we go to the coefficient, and we find that B has a 7.9 versus a 1.8 for the C, and B would be the strongest acid. Okay? Yep. All right. Just in case I make that change on exam. Won't be a big shock. I added this question just for giggles. Which one produces the strongest conjugate base? The weakest acid produces the strongest conjugate base. So that would be actually B. Because once you get to that point where you've got the second hydrogen removed from that molecule, you're dealing with Ka of 10 to the minus 12. And that's weaker than any of them. which produces the strongest conjugate base? That was tricky. I had to stop and think a minute. Number 9. Which of the following statements are true? Well, let's see. A, B, C, D, and E. And E says all the statements A through C are false. So A through C are false. We're looking for, if we can find any true ones, at least 2 of the statements are true. 2 are true. Okay. So we really only have to assess A, B, and C. All right. The pH of a strong acid is always lower than the pH of a weak acid. No. That depends upon concentration. And it depends upon the K value. Both of them together. So A is false. The pH of a solution can never be negative. It's just a mathematical formula. Negative log of the hydrogen ion concentration. All we need is one example that gives us a negative, and that was false. So let's say the hydrogen ion concentration is 10 to the, let's see. Yeah. Say it's 10 molar. That's pretty strong. Right? So the negative log of that, this would be 1, and a negative would be -1. So we found, all we needed is to find 1 to falsify that statement. So pHs can be negative. It's just it's not very useful. All right, and C, for a conjugate acid-base pair, Ka equals 1 over Kb. Yes or no? No. No. That's false. What is? If we want to find Kb, actually, let's go back to the original. Ka times Kb equals Kw. Right. So if we want to find, in this case, Ka would equal Kw divided by Kb. Now, how do we end up with this one? Well, we say, that'd take too long. Go back and look at the original in our in the lecture part. Okay, number 11. For the stepwise dissociation of aqueous H3PO4, which of the following is not a conjugate acid-base pair? Right. So if we take H3PO4, the first one is going to produce a hydrogen and H2PO4 minus. Right. So the charge is balanced. Then we take this one, H2PO4 minus, and one more hydrogen. And that's HPO4 2 minus. Take that last one and remove another hydrogen. And that's PO4 3 minus. Those are the three steps that you would go through. So conjugate acid-base pair. Well, there's one pair, there's another pair, there's another pair. So let's see which one of these is not a conjugate acid-base pair. HPO4 2 minus. So it would have to be H2PO4 minus for the first one, which is not a conjugate acid base pair. Oh, sorry, got one here too. So this would be the acid and that would be the conjugate base. So the first one is correct. The second one, H3PO4 would be H2PO4 minus. That one's correct. C, H2PO4, so it could be here or here. H2PO4 and HPO4 2 minus, that's correct. And H2PO4 and PO4 3 minus. No, because it went from here straight to there. All right, so D is wrong. D is the bad one. And the last one we threw in just as a filler. H3O plus and H2O. So these are acid-base pair. Actually, that would fit. We could put this one in all three of them. Right, this would go into here, here, and here. And this one would go over here instead of that. So it really is part of the reaction. Let's see, number 12. Yeah, okay, that's good. I didn't see myself. For which of the following 0.1 molar diprotic acids would the second dissociation affect the pH significantly? All right, so when we're dealing with diprotic acids, most will have a second dissociation. Let's see, this is Ka1 and this is Ka2. This one is going to be much, much smaller than Ka1, typically. But hypothetically speaking, if you had this one either approximately equal to Ka2 or only slightly smaller, then you could expect the second dissociation to affect the pH. So that's what we're looking for here. We're looking for the second Ka to be close to the first Ka. Now, the first one is 5 orders of magnitude difference, like -2 and -7. -4, -8 is 4 orders of magnitude. There's no influence there. 5 orders for C, only 1 order. Actually, it's even closer than that, because 1.8 times 10 to the minus 3, 1.8 times 10 to the minus 3 versus 9.3 times 10 to the minus 4. So let's make that one 10 to the minus 3. All right, that would be 0.93 times 10 to the minus 3, right? If we just made this part equal, now we can compare these two. And this one is about double that one. So the D for that acid, whatever it may be, the second dissociation does have an influence on the overall pH, simply because the second dissociation is very close to the first one. The K is very close to the first one. That's the whole point of that argument. All right, number 16. I'm sure there's some acids out there that are like that, but most of them are not. Which of the following would give the highest pH when dissolved in water to form a 0.1 molar solution? So let's see, 16. 0.1 molar solution. And we're looking for the highest pH. That is most basic solutions. Right? Okay. Let's see, we have A, B, C, D, E. The first one is strong acid. Okay. And the second one is weak acid. And the second one is potassium salt of a weak acid. So potassium A, weak acid. D is potassium salt of a strong acid. A, strong acid. Okay. And ammonium salt of a strong acid. That's strong acid. Okay. We're looking for the most basic. All right, we can count out the acids because we have some salts in here that are probably going to give us what we want. So we can say these two aren't even in the running. How do we determine? Well, let's go rule of thumb first, right? Rule of thumb. If you have a salt of a strong base and a weak acid, you should have a basic solution. So K would be from KOH, right? That's a strong base. And A is from a weak acid, HA. Right, that's a weak acid. So this should produce a basic solution. A strong base and a strong acid as their origins for the salts is going to be neutral. Okay. And a weak base and a strong acid is going to be acidic. This is derived from a strong acid. This is derived from a weak base. So you're going to have an acidic solution. Okay. So I would say C would be our best choice. Now that's the rule of thumb method. What actually happens in solution is when this one goes into solution, it produces K plus and something there. That's an aqueous solution. All right. Potassium's not going to react with water. Right? It's perfectly happy the way it is in solution. The A minus now from a weak acid is a strong base. So the strong base is going to go for water molecules and take a proton from that water molecule and reconstitute its weak acid. It wants to be here, not here. Okay. What's left over? Hydroxyls. That's why the solution is basic. But the rule of thumb is quicker when you can use it. All right, let's see, who's next? 19. Solid ammonium acetate, excuse me, gives Ka for NH4 and the Kb for C2H3O2. Oh, what type of solution are you going to get from dissolving that salt in solution? Well, in this case, we've got the source of a weak acid and a weak base, right? So in that case, when you get a salt formed from those two combinations and you put them in solution, you don't know what the outcome is going to be unless you have access to the K values. The Ka for the ammonium, because it has the ability to produce a proton. The Kb for the acetate ion, because it has the ability to accept a proton. So you compare those two, and that will tell you which one dominates. They're exactly equal. So you get a neutral solution out of that combination. That's a C. We didn't spend a lot of time on that one in class, but that's how you tell the difference. If the Kb were larger for the anion, then it would be a basic solution. If the Ka for the cation was larger, then you get an acidic solution. Okay, there's a competition. All right, number 20. Solid ammonium perchlorate. That would be fun. Ammonium, Ka is 5.6 times 10 to the minus 2, just like it was in the previous one. Whereas the perchlorate ion is 10 to the minus 21. So there we have a comparison of 10 to the minus 10 versus 10 to the minus 21. The Ka, the acid, wins. This is going to be an acidic solution. Okay? 10 to the minus 10 is greater than 10 to the minus 21. Now, if you were given, say, Ka for perchloric acid, then you'd want to calculate the Kb for the anion, the conjugate base. Then you could compare them. But if you're given Kas for both, then you can't compare them for a salt. You got to find the Kb for the conjugate base, which is the anion, just in case. 22. Which factor listed below is most important in determining the strength of an oxyacid? What's an oxyacid? Well, it's an acid that's got oxygen in the molecule, right? For instance, we could have this sequence. That's good. Well, actually, that's more accurate, because the hydrogen is attached to an oxygen. All right, which one's strongest? That one right there. The more oxygens, the stronger the acid. So let's see, which one fits that description? The size of the molecule, the most important. Now, the size of the molecule may have an influence, but it's not the most important for an oxyacid. The number of oxygen atoms present in the molecule, D, is the correct answer. That's what influences the acidity of an oxyacid. As long as it's a homologous series, right? If you throw a bromine in there, then you're muddying the water, apples and oranges. Right? But if you've got everything in here is the same except for the number of oxygens, then you can make the comparison. And this is the strongest. Perchloric acid. It has some other interesting characteristics too. Like, I don't know, heat it up with organic matter and you get an explosion. 24. Which of the species below, when dissolved in water, will not produce a basic solution? All right, so let's see what we're dealing with here. First one, sulfur dioxide, ammonia, barium oxide, and barium hydroxide, and then none of these. Question was, will not produce a basic solution. So we got a double negative, which will not produce a basic solution. Let's find out which one produced basic solutions, okay? This one, obviously, all it has to do is dissociate a hydroxyl. We got a basic solution. That's Arrhenius definition of a base. How about barium oxide? What happens when we combine it with water? Well, one of the hydrogens is transferred here. Actually, overall, that's what you get. The oxide of a metal produces a basic solution. The oxide of a non-metal produces an acidic solution. Well, let's go ahead and do this one. That's going to pick up a proton and leave a hydroxyl behind. So all these are basic. This one combined with water is going to produce H2SO3, which is an acid. Okay. All right, so the answer is A. This is the one that does not produce a basic solution. It's acidic. Okay, Lewis. We're gonna use our Lewis definitions. If I were walking into an exam as a student, I'm trying to keep them straight. Bronsted-Lowry versus Lewis. I would over in the margins, I would say, all right, Bronsted-Lowry acid base is a proton donor. And a base is a proton acceptor. Okay. Lewis would be, instead of a donor, it'd be electron pair acceptor or an electron pair donor. That's how I keep them straight. Then I wouldn't have to keep that in my mind while I was trying to answer the question. Which of the following species cannot act as a Lewis base? A Lewis base is an electron pair donor. Which one cannot donate electrons? All right, so 25. First one, O2 minus. Does it have electron pairs available? Oh, yeah. Abundance. How about OH minus? Yep, it can donate. How about CH4? Nope. We've done Lewis structures, right? Okay. So remember the Lewis structure for this one. All the electron pairs there are bound up in covalent bonds. It would not be a good Lewis base. H2S is kind of like water. Like this, there, there. So it has available electron pairs. That would be a good donor. And the last one, ammonia. Right, ammonia is like this. It can donate also. This is the one that has no free electrons to donate. So it would not be a good Lewis base. Which of the following, let's see, 26. Put it over here. Which of the following species cannot act as a Lewis base? Oh, okay. Well, you can look at the charges plus the ammonia. The ammonia's got this pair here. D, A, B, and C have excess electrons, right? They're negative charges. So they got abundance of electrons to donate. But that NH4, right, it's like methane. everything is tied up. Right? So that would not be, the NH4 would not be a good Lewis base. Okay. Let's see, what's 27? Cannot act as a Lewis acid. Okay, so we can erase these. I'm not sure why I got rid of 28. Probably had an error in it. I didn't feel like fixing it. 27. Which one cannot act as a Lewis acid? All right. A Lewis acid. Electron pair acceptor. Which one cannot accept? All right. Potassium. Well, it can take electrons. It's got a positive charge. What about magnesium? Oh, yeah. This would be Lewis acid. Lewis acid, Lewis acid. See? Yeah, I was expecting aluminum. There it is. That's a good Lewis acid. How about H plus? Yeah, it can accept electrons. H minus? No. No room. It would not be a good Lewis acid. All right. Number 30. Let's see. I'll leave that up there for now until I need the room. Given the following pKa's, determine which of the, is the weakest base of the answers listed. Okay, so let's put the answers here because I smell a rat. ClO2 minus, ClO minus, HCOO minus, and F minus, and Cl minus. Okay. We're looking for the weakest. Which of these is the weakest base? The weakest base would be derived from the strongest acid. Right? So if we just look at the information given to us, the strongest acid is HClO2, right? 1.95 Ka. So ClO2 minus, we would gravitate to this one. But if we look at our choices, this is from a weak acid, but this is from a strong acid. And a strong acid trumps all of them because HCl is a strong acid. It will produce the weakest base. That's kind of a trick question because there's no Ka. Well, Ka would be like infinity. It'd be so large, it'd be ridiculous to try to measure it. This would be the weakest base because it comes from the strongest acid. Okay? That was a trick question. Not fair. Should have left out Cl minus and put something else in there. Then you could stick to the Kas. I guess we're just trying to figure if you're paying attention. 38. Okay. Carbonic acid is a diprotic acid, H2CO3. Ka1 is 10 to the minus 7th. Ka2 is 10 to the minus 11th. The ion product for water is 10 to the minus 14th. What is the OH minus concentration of a solution that is 0.18 molar in sodium carbonate? All right. So what type of reactions are we dealing with here? Acid dissociations. So what are the major species in this reaction mixture? Well, H2CO3 for sure, because it's a weak acid, right? It's not going to dissociate that much. And water is also a major species. Let's see, what else? That's it, okay? So we just need to compare these dissociations and see which one controls the pH. So this would produce H plus HCO3 minus with a Ka of 4.2 times 10 to the minus 7. Now, do we need to be concerned with the second dissociation? No, because it's 10 to the minus 11. It's 4 orders of magnitude weaker. Right? It would not control the pH. If we settle on this one, it would not have an influence on the pH. If we compare this one, OH minus, it's 1 times 10 to the minus 14. So this is the reaction that we're interested in right here. That's the one that controls the pH. Okay. Next. Let's see. Hydroxide ion concentration of a solution that's 0.18 molar in sodium carbonate. 0. Okay. I messed up. Sodium carbonate. Sodium carbonate. Let's back up. I thought we were dissolving an acid. Start all over again. Sodium carbonate in aqueous solution is going to do what? It's going to completely dissociate into sodium ions and carbonate ions. Right. And these are aqueous, obviously. Okay. So now we have the salt of a strong base and a weak acid. So we would expect the solution to be basic. That's the first point. So let's see. I need to refresh my memory. How to approach this. Okay. This is a stronger base. Well, you know what? In solution, what reaction are we going to get? That's where we need to focus our attention. This is in solution. What's it going to react with? It's going to react with water. Right? Yeah, it's going to react with water. And produce HCO3 minus plus OH minus. Now, I'm wondering if we need to go, should we go one step further? No, I don't think we need to go one step further. I think this is going to answer our question. Now we can go ahead and let's see, are we given, we're given both KAs. Yeah, we're given both KAs. All right, but all right, let's put what we know up here. What do we know in the beginning? Right, we have a 0.18 molar solution of sodium carbonate. So what's the concentration of carbonate when we start? It's 0.18 molar, right? Because the thing is completely soluble. So this is 0.18 molar. Okay, we're going to say that this is 0, and this is, for all intents and purposes, 0. So the reaction is going to move that direction. We're going to lose a certain amount here, and it's going to show up here. Okay. All right, but the equilibrium expression is Kb, not Ka. Right. So which Ka do we use? We use Ka2. Right, because Ka2 references CO3 2 minus. And we need to actually Kb equals Kw over Ka2. So this is 1 times 10 to the minus 14, and this is 4.8 times 10 to the minus 11. I need my calculator for that one. Okay, I get 2.08 times 10 to the minus 4 is the Kb for this one. So this Kb is equal to that one, this one, divided by that. Okay, so we have x times x, and then 0.18 minus x. And that's equal to this value. Now, if we leave it as is, we're going to end up with a quadratic. So since this is a small value, let's approximate this as x squared over 0.18 and say that x is so small it won't influence the denominator any. Now we can say x squared is equal to this value times that value. And I get 3.75 times 10 to the minus 5, and x equals the square root of that. 6.12 times 10 to the minus 3 molar. What? Molar what? Hydroxyl. Okay. All right. So the closest one there is A. The question is, did our approximation affect the outcome? Right. So we go for the 5% rule. If we put the x, if we put x in here, here, and here, how close is it to this one? Right. So that's what I'm saying. 6.12 times 10 to the minus 3, of course, it's going to be squared because it's this one times this one. And then 0.18 minus 6.12 times 10 to the minus 3. And what value is that? All right. So I already got it in here. Let me square it. And then say 0.18 and 6.12. minus, and divide. And that gives me 2.16 times 10 to the minus 4. Okay. That's what we calculate as the KB with this value. All right. Is that within 5% of this value? So what we do is take 2.16. Since the exponents are the same for the tens, we can just leave those out. Minus 2.08 divided by 2.08 times 100. 2.16 and 2.08 minus 2.08 divided. So that's 3.8%. So we're within 5%. Did I lose anybody? Okay. Now the question that keeps rattling around in my head is, this is the outcome for this reaction. Should we be concerned with this reaction? That one. Well, we would want to know the KB for this one also. So this is the KB for the A2. What would be the KB for the A1? So this is 2. This would be 1. So let's just calculate that. 1 times 10 to the minus 14 divided by what's the first one is 4.2 times 10 to the minus 7. Okay. This is 2.38 times 10 to the minus 8. Okay. So this was the KB first, right? That was the KB for this reaction. This is the KB for the second reaction. What kind of influence is it going to have on the hydroxyl concentration? It's 4 orders of magnitude weaker. So it would have no impact on the outcome. So we're justified in stopping our calculation with this one as the influencer of the hydroxide concentration. Does that make sense? Yeah, it's kind of like the converse of the other one where we compare the A1 and the A2 for acids. Now we're comparing the KB1 and the KB2 for the base in the sort of the reverse reaction. And this one wins. That one would have little or no influence on the outcome. We could do the calculations, but we don't have time. And prove it. Where would you go with this one? You'd set it up with this reaction. You take these values across here, whatever the values came out to be, plug them in as initial values, and then proceed with a nice table for the second reaction and see what you come up with. And I'm pretty sure you come up with pretty close to this value. In other words, the added impact of the hydroxyls would not change that value at 2 decimal points. Okay. Enough said about that one. I don't know if I'm going to have any more Lewis ones. I guess I can leave that up there. All right. I don't know why that one's bold. I just forgot and left it that way, I guess. 39. Calculate the pH at equivalence for the following titration. Okay, 0.1 molar HOCl, 0.1 molar hypochlorous acid, with a Ka of 3.5 times 10 to the minus 8. Ka 3.5 times 10 to the minus 8. And sodium hydroxide. It doesn't have a K because it's a strong base. I think I know which way I'm going with this one. I'm just checking to see. Yes, okay. So with this titration, if we're trying to find out the pH at equivalence, we want this reaction to go to completion and see what it produces. So all right. Let's see, did I use, yeah, I kept it simple. All right, so the first step here is stoichiometry. All right, stoichiometry would be HOCl plus sodium hydroxide, and I'm leaving out the aqueous part. And this would produce sodium hypochlorite plus water. Okay. If this is 0.1 molar and this is 0.1 molar, we need values to work with here. And since they're the same concentration, we can use any value we want. I just say to keep it easy. I think I worked the problem with 100 mils. So let's try it with 10 mils. Right, 100 mils would be a little excessive. So let's say we have 10 mils of this one. Would stoichiometrically would be 10 mils of this one also, right? So 10 mils times 0.1 would be 1 millimole, right? And 10 times this one would be 1 millimole. And since there's one hydroxyl and one hydrogen, then we would produce 1 millimole here, divided by 10, actually divided by 20 milliliters, correct? Because it takes 10 of each. So 1 divided by 20 is what? 0.050 molar in hypochlorite. Because sodium's not going to be a problem. Hypochlorite's the one we want. Okay, that's the stoichiometry. Now we want equilibrium. Okay, so I'm gonna have to erase some stuff. Let's erase this one. And that one. And temporarily, I'm going to leave that one there so I don't lose track of my concentrations. What reaction are we talking about here? We're talking about this one. OCl minus plus water is in equilibrium with HOCl plus OH minus. Okay. The initial concentration here is 0.050 molar. And we're saying, since we went to equivalence, then this is 0, and this is close enough to 0. Okay. Now we can do our equilibrium calculation. We'll move that way. We're going to lose some of this. These are 1 to 1 to 1 ratio. So this is going to be plus X, and this is plus X. So this is going to be 0.050 minus X, and this is going to be X, X. So the equilibrium is based upon the KB of that reaction. Are we given? Yes, we're given Ka for HOCl. We need the KB. So that's KW over Ka. which is 1 times 10 to the minus 14, divided by that Ka, 3.5 10 to the minus 8. I don't have superscripts in there. That's a boo-boo. 1 exponent 3.5. So I get 2.86 times 10 to the minus 7 is KB. KB is equal to HOCl OH minus divided by OCl minus. Okay. With me so far? Stop me if you have questions. Okay. This is going to be X. This is going to be X. This is going to be 0.05 minus X. So we're going to, that's a pretty small KB. So we should expect to have very small X as the outcome. So we can say this is X squared over 0.050 equal to this value right here. So X squared is going to be 0.050 times 286 times 10 to the minus 7. Let's see what that is. 5 times that value. 1.43 times 10 to the minus 8. And then X would be the square root of that. 1.20 times 10 minus 4 molar hydroxide. Now the question was pH, wasn't it? Let's see, did I do the calculation for 5% rule here? No, I didn't. I just went ahead with it. We're assuming it's 5% okay. So I think the simplest way to get to pH is to calculate the pOH first. So pOH equals negative log of 1.20 times 10 to the minus 4. Take the log of that and change the sign. 3.9. Let's see. Actually, 3. I kept 3 significant figures. Actually, I really can only keep 2. 1.2, and that leaves 3.92. 2 decimal places in the pH, pOH and pH. Now the pH then is going to be 14 minus 3.92. And I get 10.1 pH. E. That was a lot of work for just one number, right? This was an example. And that's typical. If you want to find the pH of equivalence for a reaction, is to do the stoichiometry first. Let it go all the way to completion, because that's what the equivalence point says. Equivalence point is where we go to completion. Then we take what's left after that reaction and work the equilibrium to come back to the pH for that equivalence point. Now, why would we want to do that? If we know the pH at equivalence, now we can pick our indicator. Our indicator should have its pKa plus or minus 1 of that. So it should be either 9.1 to 11.1 pKa for the indicator. And if you're coming up from the acid side, you're adding base to your acid. And you have a choice between two indicators that have pKa's. One is on the low side, one is on the high side. If you're coming up from the acid side with a base, pick the one on the high side. And the opposite, if you're coming down by adding acid, then you would pick the one on the low side. It gives you a more accurate reading. Oh, that's chapter 14. So let's see. Yep. I didn't even have to stop the share. It must be sharing Acrobat and not just the file. There we go. All right, so far so good, huh? Now, chapter 15. Good on time. So far so good. Chapter 15 problems, they're probably going to take a little longer to work because we're into equilibrium heavy now. So let's go down number 4. A weak acid, hydrofluoric acid, is in solution with dissolved sodium fluoride. I smell buffer coming. If hydrochloric acid is added, which ion will react with the extra hydrogen ions from HCl to keep the pH from changing? All right. If you've got HF and sodium fluoride, that means there's your acid conjugate base. So which one is hydrogen going to react with? That one right there. That would produce some of these, remove the hydrogen from solution, and stabilize the pH. So C would be your answer there. Number 5. Which of the following is true for a buffered solution? Well, let's see. Let's define a buffered solution. One is pH changes slightly upon addition of hydrogen ions or hydroxyl ions. Okay. What else can we say about a buffer? We can say that the ideal ratio of conjugate base to the acid, the ideal ratio is 1. Approximately equal of these two will give you the best buffer. Now let's read our possibilities. The solution resists change in its hydrogen ions. Yeah, A's right. How about B? The solution will not change its pH very much, even if a concentrated acid is added. Well, that depends on how much, but generally speaking, that's true. Because you're not going to add it all at once anyway. The solution will not change its pH very much, even if a strong base is added. Yeah. And there again, we're dependent upon amount. Right? If you exceed the buffer capacity, then the buffer, you've destroyed the buffer and it's doesn't function anymore. D, any hydrogen ions will react with the conjugate base of a weak acid already in solution. Yes, we just showed that before. So all of them are true. with limitations. All right. Number 8. How do the pHs of the buffered solutions compare? It's referencing this statement up here. There we go. Let's see, buffer solution 1. Let's see. Buffer 1 is what? Is 5 molar HO acetic acid. 5 molar HOAC. That's an abbreviation for acetic acid. And 5 molar sodium acetate. Sodium acetate. Well, that would make a good buffer, right? You have 5 molar conjugate base and 5 molar acid. That's a ratio of 1 to 1. That would be a good base. How about the second one? Okay, in the second one, it appears we have a 1-to-1 ratio, but now 0.05 molar. 0.05 molar HOAC and sodium acetate. Okay. These are both good buffers. The difference is capacity. This one would have a much higher buffer capacity than that one. So which statement talks to that? Well, let's see. A and B say buffer solution 1 is greater than that of buffer solution 2. The pH is different. No. pH, remember Henderson-Hasselbalch. The pKa of your weak acid plus the log of conjugate base over the acid. Okay. So the pH is going to be the same for both of them. Right. So A and B can't be true. C says the pH of buffer solution 1 is equal to that of buffer 2. Yeah, that's right. C is true. Cannot determine? No, we know exactly what to do. All we need is the pKa for acetic acid, and we can calculate the pH. Right. So the best answer is C. Right. They have both the same pHs. The difference is capacity. Right. This one has 10 times the capacity of the other one. Nope. Did I write that correctly? Yeah, 100 times the capacity. Right. Because we move the decimal 1, 2 places. 100 times that capacity. Now, why would we want to short ourselves to make this one rather than that one? It depends on the chemical processes that are going on in solution. You may not want the ionic strength that would be imposed on the solution by this one. If it's a non-living system, there are reasons, but living systems, if you exceed a certain osmotic pressure of your solution, then you're going to kill the cells, right? And then the buffer doesn't matter. Okay. Number 9. I'll leave Henderson-Hasselbalch there. It'll probably need it again. Which of the following is the net ionic equation for the reaction that occurs during the titration of nitric acid with potassium hydroxide? Well, let's see. Nitric acid plus potassium hydroxide. This is a strong acid and a strong base. So we should get, actually it should go to completion. We form the salt, potassium nitrate, which is completely soluble, plus water. Okay. That's the molecular equation, right? Or the formula equation. But the question is, what's the net ionic equation. Well, this is in solution as plus and minus here. This is in solution, this is in solution. These guys cancel. What's left over? What's left over is hydrogen ions plus hydroxyl ions yield water. That's the net ionic equation of an acid-base reaction. Bronsted-Lowry acid-base. Okay, so E is the answer. Number 10. Let's see, in the titration of weak acid HA with 0.1 molar sodium hydroxide, the stoichiometric point is known to occur at a pH value of approximately 10. Okay, so equivalence equals pH 10. Which of the following indicator acids would be the best to use to mark the endpoint of this titration? When they say indicator, what they mean is which one of these molecules will change color at the proper time. So we want something that's very close to that equivalence point for the pKa of our indicator. And the closest one I see is B with 10 to the minus 11. Right. And notice we're titrating a weak acid with base. We're coming up from the acid side to the base. So that's right. 10 to the minus 11 is, well, the pKa, what would be, we should be comparing the pKa. What's the pKa of that one? 10 to the minus 11 is negative log of that, which would be 11. So now we can compare 11 to 10. 11 is greater by 1 unit. So it's kind of on the edge. The other option you have is to, well, you're still going to have to know the pH of the equivalents. But once you know that, then you can get that chart. And when I look at that chart that we showed at the end of the last chapter, I look at two things. One is the pKa, the pH range that it's effective at, and the color. You know, some people can differentiate colors, two different colors, better than others. Now, phenolphthalein is great because it's colorless versus pink. But there are some that actually do change color, and you got to be able to distinguish the difference between those colors. And if you're partially colorblind like I am, some of those colors don't work. Like when I stop at an intersection and the light changes so I can go, for me, it turns blue, not green. Now, I don't know if that's the light or if it's my eyes. I think it's my eyes. All right, does it look green to you? Okay, so it looks blue to me. All right, where was I? 13? 13. Which of the following solutions would be described as a buffer solution? All right, remember the buffer is dependent upon two things. It's dependent upon weak acid and its conjugate base. And so we have to have that. We know how to tell acid and conjugate base. And the ratio. Approximately 1 is the best. Okay, so which one's these? A, B, C, D, and E. Right. A is a weak acid, right? Acetic acid. That's another way of saying acetic acid. CH3COOH is also acetic acid. We write it that way sometimes because it gives us information about the structure of the molecule. If I wrote it out, it would be that methyl group right there attached to another carbon, and then we'd have a double bonded oxygen, O and H. That's the acidic hydrogen right there. So sometimes you'll see it that way, rather than C2H3O2. Okay, so A has, let's see, 0.25 molar and 0.2 molar HCl. Well, you can't make a buffer with an acid and an acid, right? So that one doesn't work. B says the weak acid plus approximately equal molar sodium hydroxide. That's a good one right there. It satisfies this condition and that condition, because when you add a base to it, it's going to strip away the acetate ion and make a sodium acetate out of it. So that gives you the conjugate base. And you left behind with some you know what? It's not the best buffer solution. You know why? Because with, let's see, this one, 0.25 molar of this compound and 0.20 sodium hydroxide. So when you put those together, this is going to consume 0.2 of that, and you got this much left over with 0.2 acetate. Oops. This is going to be the undissociated acid. So that's not the best buffer. It will work, but it's not the best one because of the ratio here. You see what I did? When you add that much base, you're changing this to that and leaving this behind. So it's not the best ratio, but it will work. C, okay, so we're saying that this one is acceptable, but not the best. C is sodium bromide and hydrobromic acid. That won't work because bromine is a HBr is a strong acid. It won't work. It has to be a weak acid. Ammonia, 0.25 ammonia and 0.15 sodium hydroxide. Well, ammonia is a base, so you can't neutralize it with a base. Now, if we combine hydrochloric acid and a weak base, you could get a buffer out of that, right? And the last one is a strong acid, strong base, and that's just ludicrous. Right? So the best one out of this whole thing is B. It's not the best possible, but it's the best one of those available. All right, 14. Which of the following mixtures would be classified as a buffer solution? Okay, let's see, what do we got going for us here? A, B, C, D, and E. Let's see if we can eliminate some. The top one is a strong acid mixed with a salt. Won't work, has to be a weak acid. All right, so that one's gone. Let's see. All right, B is a weak acid and a strong base of equal concentrations. But look at how much base we added to that acid. We added enough to neutralize it plus some, right? We're completely out of the buffer range. Right? They're equal concentrations, So if you add 55 milliliters of sodium hydroxide to 50 milliliters of acetic acid, you're gonna go past the equivalence point. Like, you're nowhere near the buffer. 0.1 molar acetic and 25 milliliters of sodium hydroxide. That's a good one. Equal concentrations, we're only neutralizing half of the acid. So that gives us a ratio of C2H3O2 versus what's left over. And that would be well, instead of doing the calculations, we probably have in the neighborhood of a 1-to-1. Roughly 1-to-1. This is a good one right here. C. And if you're pressed for time, I'll stop there. But the others, D, you don't have enough sodium hydroxide in there. You're still going to be acidic with the acetic acid. There's not enough base to put you in the buffer zone. So D is also bad. And E, what's wrong with E? Oh, you're trying, you got two acids together, right? That won't work. Right, so we found it. C is the best one. Okay, 19. Doing on time. Got about an hour, a little less than an hour. Right? Class is over at 10:25. And then the lab, 5 minutes later. Consider the following indicators and their pH ranges. Right. Methyl orange, we're given these ideal pH ranges for each of these indicators. Assume an indicator works best when the equivalence point of the titration comes in the middle of the indicator range. For which of the following titrations would methyl red be the best indicator? All right, methyl red is 4.8 to 6.0. 4.8 to 6.0 pH. Or methyl red. This is going to take some time. Why? Because we have to calculate the equivalence point for each reaction. Some are easier than others. Like, what's the equivalence point for A? Strong acid, strong base. That's pH 7, right? That would not be a good indicator, right? Rule of thumb, strong acid, strong base, neutral. How about B? Aniline plus HCl. Okay, 0.1 molar. So when we find the equivalence point for a weak base and a strong acid, then it's going to be in the acidic range. So maybe that one. And I'm trying to narrow the field so we don't have to calculate every one. This one's possible. Ammonia with an acid. Okay, that's going to be acidic also. Well, we don't know exactly what it is yet. D is a weak acid and a strong base. So that's going to be basic. It's going to be out of the range, right? It's going to be actually greater than pH 7. Okay, and E, acetic acid and sodium hydroxide. So that would be basic also. Okay. So we can focus our attention on these two, see whether it's B or C. Okay. Now, I think what we're going to have to do is, same as always, we're gonna have to, oops, I'm in the wrong chapter. 19. Yeah. 19, here we go. So we're looking at B and C. We'll try to save some time and pull this out. So B, let's see. Let's think if there's a quicker way to do this. Let's set up an ice table. All right, once we go to B, okay, so B, we've got aniline, which I'm going to call the base. That's aniline. And when we add acid to it, it's going to produce, actually, this is the stoichiometry part. HB. So now we've got HB in solution. And well, maybe, you know what? Yeah, I better leave it V because that's a base. So now we've got this base. We got the conjugate acid of the base. It's going to be plus. And what's it going to do? Well, it can react with water to produce more of the B plus H3O plus, like that. So this aniline plus our acid that we added, right, hydrochloric acid, produces this one as an outcome. So if we start off with how much here, 0.1 molar aniline, and this, we say 10 milliliters, it would be 1 millimole, would be 1 millimole here. And if the concentration of acid is the same, now we got this one divided by 20 milliliters, which is equal to 0.05 molar. So now we're starting with 0.05 molar here, 0 and 0. That's our ice table. And we got, we're going to lose some of this. And it's going to show up over here. This should give us sort of a generic equation. Once we got this value, this part of the equation is going to be the same for any one of them. Okay. But we're given the Kb for aniline. We need the Ka because this is an acid reaction. We're losing this proton. So what we need is the Ka for aniline. Kb, 3.8 10 to the minus 10. All right. Did I lose anybody yet? Okay. Let's see. 3.8, it's 10. This is 2.63 times 10 to the minus 5. Okay. So this expression now is going to be x squared over, and I'm going to say that x is too small to worry with, 0.05. So x is going to be the square root of that number times 0.05 is 1.3 2 times 10 to the minus 6. And that's square root 1.15 times 10 to the minus 3. What is that? That's hydrogen ion concentration. So the pH then is going to be negative log of that value. 2.94. Okay. That's a little low. Right? If this is 2.94 pH, it's out of the range. So by process of elimination, C is probably the best answer. So we're good up to here because we're going to get a similar reaction with C. We're going to a similar problem, only now we're going to have a different Ka. I think we can shorten the workload here. Because this is going to be ammonium, right? At equivalence. Ammonia plus acid is going to make ammonium. And this is going to be ammonia like that. So what we need here is the Ka for, no, the Kb, 1.8 times 10 to the minus 5. 8 and 1 exponent 14. So I get 5.56 times 10 to the minus 10 and multiply times 0.05 is square root of 2.78 times 10 to the minus 11. Take square root. And it's 5.27 times 10 to the minus 6. And take the negative log. And I get, oops, I messed up something. Put that back in. Right, first time. 5.28. That's the one. 5.28. There you go. So that proves that C is the best reaction of that given for methyl red as an indicator. That was a lot of work. Too much work. Too much work for an exam. I'll have to, if I use something like that, I'll have to sort of pare it down and give you information that you would normally calculate. As long as you understand why I was doing it. And even better, that you can do it if you have time. Time is the problem during an exam. If you got quiet time at home, you can work these problems probably more efficiently than under pressure. At least that's my memory of exams when I was a student. They were a pain. So you have my sympathies. Okay, a certain indicator, HIN, has a pKa of 9. So that means HIN is our indicator, and it's going to produce hydrogen ions plus IN minus, and its pKa is 9. Okay, that's given. A color change becomes visible when 7% of IN minus. When 7% of it is IN minus. At what pH is this color change visible? Okay. If it's becomes visible when 7% of it is in this form, let's see, that's in my way. pKa equals 9. We want to know what's the pH when this is 7% of that value. Let's see. So I don't waste your time. Check my approach. Oh, easier than I thought. Henderson Hasselbalch. There we go. So if we take this equation and we say pH now is equal to pKa plus the log, what are the concentrations here? Well, the ratio is you got 7% here, 0.07 here. What's down here? Down here is 0.93, right? Okay. That's what I would say. If 7% of it is over here, what's left? What's left behind is 0.93. The way I worked it here, and I haven't changed it, I should change it. Right. I should change that. Because saying 7%, if we say the ratio of this one to that one is 7%, then you would just do log of 0.07 as the decimal equivalent of percent. Okay. But the way it's worded, 7% of it is IN minus. Then what's left over is 0.93. Right? So let's see if it gets close to the answer that's given there. If we work it this way. Maybe that's why I didn't change it, because it works either way. 0.07 divided by 0.93 is log of 7.53 times 10 to the minus 2. So let's take the log of that value. All right, that's minus 1.12 and 9. Okay, so 9 and 7.88 pH. Close. But technically we could say none of these, right? Because it's off by 300s. So it depends on how you work the problem, how you interpret what's given to you. Right. So if I mark it wrong and you've produced that answer, you're that way, and my answer is different, then you can argue for your points. All you gotta do is show me your work. 26. Okay, that's getting a little weak. Not one of these. I've been upside down for 4 or 5 days. Oh, in the figure below. Excuse me. Yeah, that's our last one. So let me say, we're going to do 26 and 27. So let's say, what are the conditions for each one? Then we can scroll to the figure. In the figure below, the pH at first hydrogen equivalence is approximately pH at first hydrogen equivalence. Okay. And the second question is, the acid would best be used in a buffer near pH. So buffer. And we have selections there, 1, 4, 6, 10, and 12. 1, 4, 6, 10, and 12. pH. E. Okay, now let's scroll down. I'm gonna have to shrink it a little bit to get it all on there. How about that? Yeah. Base is on the x-axis, pH is on the y-axis. Okay, we're looking for pH at first hydrogen equivalents. It looks to me like, what type of acid is this? Does it say what it is? No, it doesn't. We can deduce what type of acid it is from its curve, right? It's got two equivalence points, C and E. That means this acid is diprotic, has two protons. Okay, the first one comes off at pH 6. That's where C is. The second one comes off near pH 12, just under pH 12, maybe 11.9. But that wasn't the question. I'm just pointing that out. Okay, how about the buffers? Where do we have buffers? Well, the first buffer is at B, which is about 2.3, maybe 2.3 or 4. Right, that's not on there. The second possible buffer is D, and it's close to 10. It's like 9.8 or thereabouts. That's close to 10, right? Pick the best one. That would work. That would be an acceptable buffer pH for this diprotic acid. Okay. So C, 6.02. Yeah. That would be acceptable. And 27 would be D, 10. Okay.